Okay, hello everyone. So today we have the third lecture. That's fun that a few people are not here today, those who were the previous time, but we have some new students. So let us first start with what we discussed the previous time, just revise a bit, and for the newcomers to get the idea of what we're speaking about here. So in general, this course is about natural language processing. So theoretically, we try to analyze how all those large language models operate, how they work, what is behind them. And in practice, in the second part of the course, we will do a small project. If you do all the tasks by one, the portfolio will make this project. And the idea is that it's not reliable to use just general GPT in your research, because GPT processes all the data from the internet. It's not just processing scientific articles. And for your research, of course, you need to rely on scientific materials. And so next lecture we will look through a few programs which help researchers to analyze articles quite fast, but still if you put questions to those programs, then you get the answers generated by AI, but they are generated on the basis of scientific articles. So this is more or less reliable. And at the same time, in the second part of the course, we will try a few open libraries, and we will start working with code snippets today to somehow work with your own corpus of articles, scientific articles. It might consist of just 10 or 20 articles, or better, hundreds of articles if you find time to get such a library for yourself. And then we will analyze them from the angle of the language, trying to figure out some tendencies. Is it clear, the general idea? And those who were here the previous lecture, will you remind me, we were discussing some semantic fields, yeah? So the relations which lie behind the words, yeah, because a large language model like GPT, it analyzes texts looking at definitions of words, or what better? Context, exactly. So if the model, the machine, just analyzes the definitions of words, the thesaurus or dictionary, then it's not, it's the quality that we had 10 years ago with machine translation. It's mostly word-by-word, rule-based translation or rule-based generation. But up-to-date generative AI, it analyzes the text, it analyzes the word, any given word, analyzing the context around it, relying on some linguistic relations. What kind of linguistic relations did we discuss last time? Exactly. Absolutely. So let's discuss it in more detail now. So what does it mean, syntagmatic relations?
It's how words collocate in the sentence.
Exactly, yeah, the collocations, because here we have international students, we all have different mother tongues, and it's quite natural for us in our language to choose the correct collocation. For example, we discussed with you that we will never say, we will say heavy rain but strong tea. And if we are an English-speaking person, it would be quite natural for us. But if we learn a foreign language, we need to learn these particular collocations, because these are the syntagmatic relations. And machines nowadays, which process language, natural language, relying on context, they can figure out what collocations you need, yeah, how to generate texts with normal collocations. What about, these are kind of horizontal relations between words and lexemes. What about vertical relations? How do we call them?
It's a substitutional relationship
Uh-huh.
between linguistic means like
Mm-hmm. Absolutely, yes. So paradigmatic relations, they help us to search for synonyms, to group words somehow, and so on. And so those syntagmatic and paradigmatic relations between words, they are analyzed by machines, but of course a machine, even a very good pre-trained transformer like GPT, it cannot understand the words like we do, because it's not a human brain yet, as far as we know at least, although it is able to solve some maths problems. But still, as for the cognitive aspect that we discussed during the first lecture from the cognitive linguistic angle, it's slightly different. So still, each word or lexeme is a token for the machine, so it's just numbers. And then it draws so-called embeddings, the topic of our today's lecture. An embedding is a vector, an arrow between words, and each word in a text, it has a lot of such arrows, a lot of embeddings, which reflect different relations, different linguistic relations, and that makes a multidimensional space where the word exists, yeah, and that helps the distance between words for the machine to choose the better word in this or that case. And so today we will discuss not still large language models, but we will discuss the first language models of the generation of 2010s that were the first to create such embeddings to analyze texts. And then next time we will proceed with up-to-date transformers like GPT, like BERT from Google, and so on, to then use them while analyzing scientific texts. And as for the home task that I hope a few of you did before this class, so I've already checked everything that I got before today, and I really liked a few parallels, a few equivalents which you gave, analyzing those examples from the book of natural language processing. For example, in one work I came across the parallel between the reviews that were given in the book, the sentiment analysis of the reviews, and the analysis that happens on different maps, because we all use maps every day. And of course, if everything is added, what people want to add there, it would be just rubbish, a lot of text. But of course, they are analyzed, they are structured by neural networks. That is how it works. And as for machine translation, we will have a specific lecture on it, because while looking through your answers, you had the opportunity to choose one of the examples, and most people selected machine translation, because really we use it every day, and we will discuss it on a separate lecture in 2 weeks, I do believe. So, what we will discuss today is vectors, the ways how models can vectorize words, draw those embeddings, trying to analyze context, relationships between words. So the ways how from different angles it is possible successfully or not so successfully to figure out which words are closely related and which are not. So to figure it out, we will start with some theory of latent semantic analysis, the procedure behind almost all those models. Then we will try out two very simple vectorization techniques, which are called bag of words, BOW, and TF-IDF, which stands for term frequency inverse document frequency. So we will try little code snippets today. I do believe that that would be the only lecture when we here run some code, just for you to try it out, because we're not going to become programmers after this course, for sure not, and it's not a prerequisite. But still, it is possible for all of us nowadays to use some simple libraries, open libraries, to analyze text. And it is a good idea to try something out, to see, to understand, to get the idea behind it. And then we will proceed with trying out these first language models. They partly use the same vectorization techniques, but they enhance them. And afterwards, we will discuss with you on your examples that you will choose, your text, which of those models is more effective or not. And we'll figure out whether your opinion will be the same as like for many researchers and data scientists or not. So, latent semantic analysis. So once again, semantics, what is it about? This branch of linguistics. Absolutely. So it is about vocabulary, about meanings, about trying for the machine to learn, to figure out this word meaning connection, yeah? And so latent semantic analysis means while doing this procedure, the machine tries to figure out some hidden meanings of the words, because it's quite easy for the machine just to choose, for example, the first definition of a word, or to choose the definition which is most frequently used. But it's not always the correct answer, yeah? It all depends on the context. And so while doing this latent semantic analysis, they try to weight the meanings which stand behind the whole context, to figure out some hidden additional meanings or specific for this context. And so to do that, by the way, do you remember the previous lecture, the last thing that we discussed was vector space model. Yeah, the model where there were a few embeddings, a few vectors drawn, and so they correlated with these collocations and so on. And this vector space model, it works with term document matrix. Do you remember the example with Shakespeare's plays? Where we had just a table where a few plays by Shakespeare were enumerated, and per each play it was analyzed whether a word, a keyword, a topic word is often used in it or not. In that case, just the frequency was counted, which is quite a straightforward procedure. Yeah, and for example, we found out that the word battle was used far more in Henry V than in other plays, which were comedies, for example, that reflected the content. And so this term document matrix, it includes documents and terms, and it enables us to compare which term is more important per each document. So in that particular case, each document was a Shakespeare's play. But in other case, it might be an article, it might be a post on a social network, or whatever. It depends on the peculiarity of the data set of the corpus that we analyze. And so just to work with this term document matrix, we can use latent semantic analysis to figure out these hidden meanings in a particular document, in a particular corpus. And then, just to make it easier, let's put it like this, we can use three matrices to figure out these hidden meanings of the words, the concepts which stand behind. So the first matrix here is about documents and concepts. The last one is about terms and concepts, how they correlate. And in the middle, we have the diagonal matrix, which shows us which concept is more important for which document. So thanks to latent semantic analysis done like this, we can figure out not just the terms like we did in this case with Shakespeare's plays, terms meaning words, but we can figure out the concepts behind the words that are important per particular document. Because of concepts, that's a good question, because a few words might mean something similar. For example, synonyms used there, like, okay, if we take 5 articles on neural networks, there would be, what can be used? In most cases, artificial intelligence might be used as a synonym to neural networks. And so if we analyze concepts, then we will get that these are synonyms, and so we will count them together as one concept. And vice versa, we can figure out that one word can stand for 2 things. In the same articles, machine learning might be in some cases used as a synonym to neural networks, and in some cases, as it should be, as the process of learning, as the method. And so then we will distinguish between those 2 concepts and count them differently. And so the only way to figure out whether those to analyze those syntagmatic relations is to analyze the context, and to figure out in which case the word coincides with a particular concept behind it. Clear? Yeah, right. Let's go on then. So this is kind of theoretical basics, how this context analysis happens. And I will quote today 2 people from the Stanford Natural Language Processing School, and this is one of them. And according to him, as you see, the vector encodes the meaning of the word, relying on the so-called distributional hypothesis that again was mentioned in the previous lecture, meaning that similar words appear close to each other. I would like to draw your attention to the word encodes here, because during this lecture and next one especially, we will discuss this process of encoding and decoding all the time, because modern transformers like GPT, they have both sides always, but still normally one of the sides is more important. For example, BERT by Google, it's called an encoder transformer, because the main aim of it is to analyze text, is to somehow figure out those concepts from tokens, from words. Whilst for GPT, it is the decoder transformer, which main aim is to generate text, to decode then back from the concepts to words. Let us now try and these techniques, these vectorization techniques, and if you follow this QR code, you will open my collab, and at the same time, if it's more convenient for you, you can just open the site of our course. So first follow the link. In both cases, you will find the code, the snippets of code that you will now run. So for the newcomers, this is the Wi-Fi status, and from 0 to 9, this is the password. It's not very fast, but we will use it just once for today to try running the code together for those who has never had such an experience. So you either follow this QR code, or you can just open the site of our course, and here you will find already the notebook, the Jupyter notebook for today's lecture. It is available, and when we open it, you will find there the code snippets. Simultaneously, I will ask you to enter your Gmail account if you are not there, because we will use, and you will use during the course, the Google platform to try out different open libraries. The platform is called collabresearch.google.com. So this is a platform which is free, which is available as all other Google resources from your Gmail account. This is a Jupyter notebook, and as you can see from the name of it, the audience, so it is done for us, for researchers, because it is impossible to create an application or a bot on this platform, but it is possible to check some hypotheses, just to run a code once, to, in our case, to process some texts with some open libraries. So you need to have in one tab either teaching site with notebook 3, and here is the first code snippet, which is called bag of words. You can as well open it if you follow the QR code on my collab. And then in the second tab, you need to open your own notebook, Collab Research Google.com, with your Gmail account, to copy code snippets from my notebook to your own one. So take a minute to open both tabs, and we will discuss those vectorization techniques. The third thing that you need to open here in the third tab is to copy a text of any in the song or poem, doesn't matter, just a little text. Of course, it won't be pure natural language processing, but it will give us opportunity to rather fast try out the models. Let us discuss the vectorization techniques. So the first two, bag of words and TF-IDF, these are the basic ones to create those embeddings, those vectors between words, the vectors that reflect the distance between words, relying on different linguistic factors, vocabulary, grammar, and so on. So the first technique that we will try out is bag of words. It's quite simple, but still used in some cases even now. The idea is that the model here helps us count the words in a document, skipping its grammar, the amount of the word, of the same word, the frequency of the same word in the document, the place of it. The only thing that is important for this model, for this technique, is that the word is in the bag of this document, that it is here. Then it will put 1. If the word is not, then it would put 0. So to run this, to use this technique, we will imply this SkeLL library. So you're welcome now to copy.
We don't need to install SkeLL library.
No, we just, you can just copy the whole text, the whole code from here. If you work on Google Colab, then you don't need to install it. It is integrated. And so let me run the code with my example about Peter Piper, and then you will run it with your own example. So simultaneously I will copy, like you do, the new text. And so in my example, you can see that in the first place, the model gives us the values as settled here in the print, the values per each word. As my text is lined, so each line comes a separate one, then it gives us information whether in each line which words exist or not. And then just alphabetically we get the list of all the words that are in our bag, in this document. So this is the line where we ask to give us all the words. So let us now put new lyrics here like you do. By the way, you need to put 3 apostrophes before and after your text for the machine to see that it is the whole text, that it is a so-called string, meaning not a command but a text. And so let's run it once again, this code. And then you get your own results. And here you can see that a few words in these lyrics are used a few times. And here is the whole list of the words that exist in this bag of words. And of course, it doesn't make much sense to use this bag of words technique if we speak just about a few lines of text. But if we speak about, I don't know, the War and Peace, we can easily, in a few seconds, get the whole vocabulary from a huge corpus.
Analyze the vector 0 and 1's. How much know what to say?
It means whether this word exists in this particular place of the document. So in the first case, each line was in apostrophes in my text, and so it analyzed each word from the vocabulary list, whether it is in the line or not. And now it analyzes the amount, the number of these words in the whole text, as we give it as a whole text. For example, it means that, which word shall we take? The word all is used twice here, the word all right once, and so on, just this alphabetical order. So do you have the result? Yeah?
In the case that it was in teaching, word if was 0 once in text.
But in that case, as it were separate lines, so it analyzed it in each particular line. So in, let me come back here. So in the, here, the word, yeah, the word if, we have the word if only in one line. Here it is. So this one stands for if.
And 0 means that the word Peter isn't in line 1 before.
No, 0 here means that there is no if here in the first line, in the second line, and in the fourth line. So here the numbers stay. The first one is for Peter, the second for Piper, the third for picked a pack of pickled peppers. And then it figures out that there are no words in the cases where we have them in the last line. So it compares the lines inside it. Yeah, absolutely.
What in 1?
1 here means that there is a word in this place, and 0 means that there is no word in this place.
He divided it by spaces.
Yeah, absolutely. Right, so did you get the result? Is the Wi-Fi fast enough? Okay, then let's proceed with the second technique, which is, let us add something to this one, which will make a bit more sense. So let's copy this line, n-gram range 2. So n-grams, these are the combinations of words. So if we take 1 gram, then we just analyze one word. If we take big-gram, then we analyze expressions of 2 words. So if we add this line about big-grams here, after the count vectorizer, then you will analyze the not just particular words, but you will analyze the expressions.
In the previous case, word if was the most common in this text?
Now, the word if here is just in alphabetical order in the first place. That is because it's quite a simple one. As for the most important words, we will look with the next models. So here it's just that the word, this list means that the word if was presented somewhere in the text, doesn't matter where.
Where is word a?
It just skipped it because it's an article. So it.
How understands what an article?
This is about preparation of the text. Do you remember we discussed with you that the content words are not the most frequent, and so the only thing that it skips by default here is articles. So that is why if we count the amount of words in the line as we did with you, A is not counted. So we have here 1, 2, 3, 4, 5, 6, 7. 7 words in the first line. 1, 2, 3, 4, 5, 6, 7. A is not counted at all.
How the machine understands what is not?
But this is the question of preparing the text that we will do with you, because if we analyze barely the text, then we will get always the results that A, of, and stuff like that are the most frequent, and by some models the result would be like the most important words, but it's not true. By default, unfortunately, this model extracts just the articles. So it knows that, okay, articles do not matter. We shouldn't count them at all.
So this is model, and the model is encoded and embedded now.
Yeah, this is the easiest one. It's
But it is not
Uh-huh.
a single content function in word.
sorry?
It is not trying to count words like 1 to 3.
Mhm.
It is an embedded. It is something from machine learning.
Yeah, this is the first step, so to say. If we now compare it to TF-IDF, you will see how it tries to weight the meanings. And here it just finds out whether something is presented or not. So if we add here to count vectorizer n-gram range 2, then it would analyze not particular words, but big-grams, meaning the expressions of 2 words, whether they are present in the text or not. Okay, meanwhile it's running, let's already discuss the TF-IDF model method, and then we will see the result. So if we go on with TF-IDF, then here the difference is that it analyzes the term frequency in a particular document and tries to compare it to the whole corpus of documents, which makes much more sense. And it is inverse IDF, so inverse document frequency, because it's obvious that, again, function words would be the most frequent. So we need to take the inverse frequency of the documents, in all the documents. So TF, term frequency, is counted from frequency of word in a document divided to the total number of documents. Something similar we did with you when we searched Национальный корпус русского языка, National Corpus of the Russian language, and we saw those IPMs that the dog is more frequent than the cat, as you remember, per all the total number of documents, millions of documents in this corpora. DF is the document frequency, it's obvious, but the whole thing takes IDF, inverse document frequency, just to avoid function words getting the highest scoring in this procedure. So let's try this out. So here we will use this SkeLL library.
If we try to run this on our machines, we should install SkeLL.
You can run it in Collab, yeah. In Jupyter Notebook, on site you won't be able to do it. So, yeah, by the way, we got the list of expressions of bigrams that the document has that are presented in this particular song, which makes a bit more sense because if we have the collocations already, we can do something else with that. Okay, let's run the second code, TF-IDF.
In this case, these allocations have sense, or it is randomly?
It just formally figures out which expressions exist in the text.
How would understand this?
It just formally takes all the words which go one by one. So it doesn't figure out meaningful collocations. It just gives us all the collocations.
No, without articles.
Without articles, yeah. Yeah, it won't give an old, yeah, it's obvious that for it that we shouldn't count it, but all the other words which go one by one, for example, such rubbish like on you, yeah, that I have in the song, it would count it because formally these are two tokens. Did you get the list of bigrams? Yeah, right. Then let's go on with TF-IDF. So here let me first add the text, the new text. So you first copy the code from site or from my collab, then you add your own text, and then you run the code. And here it is. Here already it tries to weight the words with those numbers according to their importance, not just frequency in the document. Because, for example, the word all, as we remember from the previous code, is used just once, but still here it gets 0.05, which is more than all right, for example. So the weight is.
In example from teaching, we have 4 lines in answer.
Yeah, because each line again is analyzed separately here. So if you want it, you can do the same with your text, yes, so just adding the apostrophes and then you will get the value of the words per each line. And the same happens if you compare documents. So if you compare a corpus that you will do in a few weeks, you just add here, just a moment, it will appear. You just add here to Google Drive some documents, and so if there are a few documents, then it would compare all of them, and if it's just one corpus, so it would give just one line results. So you add to this sample data, you upload the documents that you need to analyze in TXT format, and so the same will happen with not just a few lines, but with a huge corpus. So then after you've uploaded it, you need to copy the path here and to add this link to your variable just here, and then it would analyze all the documents. So have you got the values from the TF-IDF? So do you feel the difference that in the first case it's just the presence of the words, and in the second case it's already an attempt to weight whether something is more important for the document or less important? These are the basic techniques, the basic vectorization techniques, and in fact nowadays most neural networks, they use TF-IDF technique, of course. And now we will go on not just with those techniques, but with the first language models, which in fact somehow were successful in finding those weights. So here is Thomas Mikolov, who in the year 2013, together with Ilya Sutskever, you remember we discussed him during the first lecture, he launched this word-to-vec model. So nowadays they normally use much more enhanced models like voice-to-vec, text-to-image, and so on, tensor-to-tensor, and stuff like that. But this was the first thing to figure out those semantic features. And according to Thomas Mikolov, the words king and queen, they exist on the same distance from each other like men and women from queen will be on the same distance as man from king, and so on. So grammar is counted as well, not just the vocabulary like in TF-IDF, like in BOW, like in bag of words. Word-to-vec model, language model, uses two vectorization techniques. So the first one is called continuous bag of words. So it comes from the bag of words that we discussed with you, and here from the context, the model tries to figure out the target word. So it's like filling the gaps task, yeah, when you need to add a particular word. Skipgram is the opposite. It has the word, and then it needs to go on with the story. Yeah, it needs to find the context of it. So the choice of one of the architectures depends on the task that the model has, either to find a particular word or to generate some additional context. Okay. No. Yeah, just for you to relax a bit, do you want to now play a game with a quiz on Pushkin poetry? Just trying to play this game to guess the next word. Okay, what about your results with Pushkin poetry? Don't want to share? Okay, let's proceed with our models. So anyway, if we speak about word-to-vec, then the idea of this latent semantic analysis is to analyze context, but it depends whether we analyze the context might be like a full page of text, but normally it is called the window, and the window might consist of 2, 3, 4 words or tokens in a row, so before the word and after the word, to be analyzed. And the important thing is that if we speak about word-to-vec model, it is supervised. So all the parameters, including the window, so the context, the amount of words, the number of words that is analyzed, it is always kind of supervised by a human. So the human gives the parameters, and this is the example of supervised learning. So let us try it out. so coming back to the notebook, let's copy here the snippet. Yeah, but before we use Word2Vec, we need to split our sentence into separate words. So will you first copy this code snippet, which is kind of preparatory, a sentence split for the modal, and then you add your own text here, and you will get just the words, the sentences which are split by the words. While it's running, we can take the code snippet of Word2Vec, which will create embeddings of the words with the help of GenSim library. And here we will ask it to print the similar words, the most similar ones. So you then copy for this code all the words that you got from the previous result and add them here just as one line, yeah, one string. And so then we get, the main thing is to add the keyword for the text here, just for the modal to figure out the closest words from this document to the keywords that you figure out. For example, I would choose from my example pickled. So you here add the words that go separate from the previous one, and then you add here the key, so to say, the keyword for your poem or song. And so the closest one to pickled here is peck, then goes the article, still analyzed here, Piper, and so on. Whether it is close or not. So of course here it's just analyzing one document, and if it is compared to another documents of the similar type, then it makes more sense in searching for the weight of the word, not just for one document, but for the whole data set. So it compares whether this word is the closest one just in this document, or to whether it is the closest one in the whole corpus. Not only just frequency it's bag of words, and here it counts also some grammar and vocabulary relations, like gender, for example, with king and queen. At least according to this model. Sorry?
It makes a vector.
Yeah.
And how
it just counts the numbers, the distances between, but it presumes that the distances should be the same according to the same criteria, according to the same parameters given. Like, for example, gender in this in the first example with king and queen. Yeah, it is inside the library, yeah, all those parameters, because this is the example of supervised learning. The second researcher from Stanford, from the same natural language processing team, Christopher Manning, he explains that if we use just supervised models within those context windows, then we can lose something, lose some information due to some peculiarities of the document. That is why in Stanford, in the year 2014, a year after Word2Vec appeared, they launched another model, which is called GLOVE. We won't run the code because we need to use a huge corpus of GLOVE itself to upload it here, just for the model to analyze the word from the corpus. So GLOVE unlike word-to-vec, is absolutely unsupervised. The idea is that in word-to-vec, we give the parameters, we give the corpus of the documents, and the model just processes something within this corpus. Whilst GloVe doesn't have the parameters, but it has its own huge corpus, and it compares your particular document, the word which you need, with the whole corpus, and so it's kind of data-driven. That is why we won't try it now, because the Wi-Fi is not fast, and you need here to...
Its corpus doesn't contain a theoretical Russian language.
For Cyrillic language, we will compare some other, but GloVe doesn't. GloVe works mainly with English and some other European languages. Here it is. So you add the corpus here, and then it compares your word to the whole corpus and gives kind of not synonyms, but the words which come the closest according to the whole corpus. So now the question to you, what do you think, which model is more effective? For example, we need to launch a bot which will serve as a bot in our chat, help you with the course. What do you think, which model is better before the transformers? So pretending that it is the year 2015, the supervised one which has the parameters, or the unsupervised one, absolutely data-driven, which will work better with a bot that helps you, that will give you some answers, how to register on the site and so on?
It does the right, because if we need to answer one exam and our data is static for this subject, the unsupervised model would be better for us. Because it doesn't contain data that our teacher gives us. But if we want to something not for studying, supervised model would be more accuracy.
Okay, that's quite reasonable. But just in general, what do you think? Which before the transformers appeared in the year 2019, for a few years, those two approaches were used with these particular models or with their equivalents. What do you think? In most cases, for sure, we need to figure out each particular case, and in fact, data scientists normally tried out both approaches. But what do you think, in most cases, which one was more effective?
Unsupervised.
Why do you think so?
You don't need the label, so it comes automatically.
It's more convenient, for sure, and money, you can just not spend so much money on labeling, that's true. But in fact, the idea is that data scientists and researchers tried to compare both those two approaches, and in each particular case, it was a surprise why this or that worked better. So even with similar educational bots, in some cases, supervised still will work better. And the human didn't find out whether this or that approach is better, whilst the transformers inside themselves on the layers of encoding and decoding, they somehow figure out which is not better, because of course nowadays they use transfer learning, reinforcement learning that we'll discuss next time in more details. But still, they are mostly supervised or mostly unsupervised. They try to mix up both methods inside them, and they do it quite successfully, as we can see now. Right, so I'm not sure if we have enough time for the FastText to check it out. Let me just introduce it to you. So, there were a few equivalents created in 2010s of just these simple language models, and one of them was FastText. The main difference from the previous ones was in that the token normally was a syllable. So it analyzed not the words, but the syllables which go one by one. So it was a bit another approach if compared to word2vec. And so the results in some cases are more kind of accurate. So the last thing for today is for us to try to use a user's machine that will give us the results of that process of vectorization. And that would be SkeLL. Have you ever heard of sketch engine or SkeLL? Let us now try it, because in fact it's quite a good tool. So sketch engine, it is a corpus manager. It is not free, but we will use just the site created by it, which is called SkeLL. And now with the word sketch feature, we will see how we get the results of those vectors. So will you now open the site which is called SkeLL? And so then you just search for a word. You can choose here whether it is in English and Russian. I'm not sure that it still has Russian now, but still some European languages. And so then you get some examples of the usage of this word, like in Russian National Corpus. Then you get the similar words, which means synonyms. But the most interesting feature here is word sketch, where you get collocations based on vectorization process. So these are not the most common collocations, but with vectors they analyze the closest ones. So will you now try it out if you have the opportunity? Not only for English, so a few languages are available here, a few European languages you can choose. And this tool has, I would say, the best illustrations for this word sketch, illustrating how collocations are chosen. So you can choose which collocations, which parts of speech you are looking for. And then you get the closest ones based on vectors. Okay, so I would say that this is quite a useful tool, in fact, if accessed with VPN, because it's much more reasonable to learn words not separately but in collocations, and it makes more sense not just to learn the collocation from a text that you get, just this one, but relying on those vectorization process to learn the most useful collocations, so to say, for this or that lexeme. So thank you very much for staying here. That was, I would say, the hardest and the most tedious lecture of the whole course, because we tried with you a few models, just the basic ones, and then further, so if you have any questions about how to deal with those code snippets, you are welcome to come up after the lecture. So we will, I think, I will transform a bit the task, relying mostly on BLUF, probably not SkeLL itself. And next time we will discuss partly the transformers, and then we will try out a few tools. I will check up the availability of them that particular day. And we will try those tools which help us to get the summary of some articles, which help us to get the articles that include the answer to our particular question, not just the keywords like Google Scholar, for example. Okay? Right. So sorry for the technical problems and for the slow internet. Have a good evening. Bye-bye.